This is Algebra Lesson 4-6, Formalizing Relations and Functions. Now, it's really important that you understand the difference between a relation and a function. So, we will go through this vocabulary, and I will be pretty explicit in explaining how this vocabulary relates to our lesson. A relation is a pairing of numbers in one set called the domain with numbers in another set called the range. It is often represented as a set of ordered pairs. Pretty much anything can be a relation. You can have x comma y, you can have an x and y value could be like -2, 3, 4, 6. Those are relations. The domain is the possible values for the input, otherwise known as the x value. This is also the independent variable. So if I had a set of relations, let's look at this. If I had a relation where I have -2, 3, 4, 6, and let's go with 9, -12. My domain would be all of the input values, otherwise known as all of the x values. So if I wanted to find my domain here, my domain would be -2, 4, and 9. And you always put your domain in order from smallest to largest numbers. The range are the possible values for the output, otherwise known as the y value. These are dependent. This is your dependent variable. So in the same relation up here that I have in red, the -2, 3, 4, 6, and 9, -12, the range then here for this particular relation, it would be -12 because that's the smallest number I have. Then -2, that's the next smallest number I have. And then, actually not -2, -12. That was terrible. -2 is x. -2, and then I would have 3 and then 6. That goes in order. So the domain is all of the x values and the range is all of your y values. Domain is independent variable, range is dependent variable. One way to tell if something is a function versus a relation is to do something called the vertical line test. It's another way to determine if a relation is a function. Every function is a relation, but not every relation is a function. It's kind of like the thing, every poodle is a dog, but not every dog you meet is a poodle. If a vertical line passes through more than one point of a graph, then the relation is not a function. And we'll go through that in a little bit more detail a little bit later. And last but not least, we have function notation. That's writing a rule by replacing y with the term f of x. It's written f parenthesis x. It does not mean f multiplied by x. It literally means f of x. Right, the function of f at value x. That's what it stands for. Okay. A function is a special type of relation in which each value in the domain is paired with exactly one value in the range. What that means is if I have an x value of 1 and a y value and it pairs with a y value of 2, if I have another x value with 1, it cannot pair with another number and still be a function. It would not be a function if 1 paired with 2 once and 1 paired with 6 the next time. So there are several ways to determine whether or not something is a function. One is what we call a mapping diagram. And a mapping diagram, you basically take your numbers and you map out the domain in the left-hand, it's kind of a rectangle-ish shape, and the range in the right-hand shape. So we're going to identify the domain and range of each relation. We're going to represent each relation with a mapping diagram, and we're going to see if the relation is a function. We're going to do several things with this. So this would be my domain, and this is going to be my range. Remember, domain is your x values, and range is your y values. So I have 4.2, and I have 5, and then I have 7, and then 4.2 repeats itself, so I don't need to write it down twice. Okay, I'm going to put my range values in here from smallest to largest because I put my domain in from smallest to largest. I'm going to do the same thing with my range. My smallest range is 0. Then I have a 1.5 and a 2.2. And last but not least, I have a 4.8. We've identified the domain and range. Now we're going to map it out. 4.2 pairs with 1.5. But it also pairs with 0. It pairs with 1.5 here. It pairs with 0 there. So it has two different range values. 5 pairs only with 2.2, and 7 pairs only with 4.8. That's what's called a mapping diagram. So if I needed, I mapped it out in a mapping diagram. My domain, and I can just abbreviate that with a capital D. My domain is 4.2, 5, and 7. And it always goes in these funny little braces. My range from smallest to largest, 0, 1.5, 2.2, 4.8. The last thing I have to do is I have to determine whether or not this relation is a function. Okay? And in order for a relation to be a function, if it has an x value paired with a y value, and that same x value comes up again, it has to be paired with the same y value. I can see that 4.2 is paired with both 0 and 1.5. Therefore, this is not a function because the domain of 4.2 is mapped to two different range values. The domain of 4.2 is mapped to two different range values. So it is not a function. Okay, let's look at the second problem here. -1, 1, -2, 2, 4, -4, 7, -7. Okay, so I'm going to look at my domain and my range, and I'm going to abbreviate them this time. I'm going to put D for domain and R for range. So all of my x values going from the smallest number to the largest number. My smallest x value is -2, then I have a -1, then I have a +4, then I have a +7. My range values also going from smallest to largest. I have a -7, a -4, a 2, and a 1. Now I'm going to map them out. 2 goes to, or excuse me, -2 pairs with 2. Okay. -1 pairs with 1. That's down here. 4 pairs with -4. That's over here. And 7 pairs with -7. That's up here. And if we look at this, we can clearly see that there is no value for the domain that pairs with two different range values. Every domain has one range and only one range. So I can give my domain and range. My domain is -2, -1, 4, and 7. And my range is -7, -4, 2, and 1. Now, when you do your mapping diagram, you don't necessarily have to put them in order from smallest to largest, but I just like to because then when I list my domain and range, they're already in smallest to largest. Okay, so this is definitely a function. Okay, because each domain value is mapped to only one range value. So it is definitely a function. Okay. Remember when we went through the vocabulary, I said if a graph passed a vertical line test, then it was a function. I'm going to get into that vertical line test now. You can use a vertical line test to decide whether a relation is a function or not. If any vertical line will pass through more than one point of the graph, then the relation is not a function. Remember, a vertical line is an up and down line, not a side-to-side line, but an up and down line. So if it says identify functions using the vertical line test, is the relation a function, use the vertical line test. The first one, they give us points, so we can just plot those points. So I'm going to plot the point -4, -4. I'm going to plot the point negative 2, 3, 3, 0, 5, 1, and 6, 1. So negative 4 goes here. Negative 2, positive 3 goes here. 3, 0 is here. 5, 1 is here. And 6, 1 is here. Now, if I was to draw vertical lines, and I'm going to draw some vertical lines that are, I'm going to draw some dashed lines because I think it makes it easier for you to see this. And I'm going to draw them in red. Okay, if I draw a vertical line here, it does not go through my any other point but that one point that was in blue that I just obliterated. See if I can get this to be a little bit thinner. There we go. Over here, if I draw this vertical line, that's a terrible vertical line. I need to learn how to draw straight lines better. Let's do both of those better. So let's go with that. Let's go with that. And let's go with this. So if I have a vertical line here, it goes through one point. If I have a vertical line here, 1 point, here, 1 point, here, 1 point, here, 1 point. It only goes through each part of the graph one time. It does not go through multiple points. One vertical line does not go through multiple points. Each vertical line goes through one and only 1 point. That means this is a function. Now, letter B here, in order to figure out if it's a function, I'm going to have to make a table of values. Because they didn't give me points. They just gave me an equation that I have to solve. Okay, so I'm going to use some points here. I'm going to use negative 2, negative 1, 0, 1, and 2 because those are my favorite points to use. And we're doing 2x squared plus 1. So 2 times negative 2 squared. Well, negative 2 squared is positive 4. 4 times 2 is 8. 8 plus 1 equals 9. 2 times negative 1 squared. Negative 1 times negative 1 is a positive 1 times 2 is 2. 2 plus 1 is 3. 2 times 0 squared. Well, 0 times itself, it's still 0. 0 plus 2 is 2. Excuse me, 0 times 2 is 0. 0 plus 1 is 1. 2 times 1 squared. 1 squared is 1. 1 times 2 is 2. 2 plus 1 is 3. 2 times 2 squared. 2 squared is 4. 4 times 2 is 8. 8 plus 1 is 9. So I have all my values. Okay, so if you remember, this is a U-shaped graph. We talked about this before. If something is to a power of 2, it's going to be a U-shaped graph or an upside-down U-shaped graph. This is a typical U-shaped graph. Negative 2, 9. So I go to negative 2 and up to 9. That would be here. Negative 1, 3. That is negative 1, 1, 2, 3 right there. 0, 1 is right there. 1, 3 is right here. And positive 2, 9 is over here. I'm going to graph this with a nice smooth curve like I'm supposed to. And of course, I should let y equals 2x squared plus 1. Okay, I'm going to check to see if the vertical line test fits with this particular graph. So I am going to see if I can pass a vertical line. I'm just going to draw some random vertical lines. No matter what I do, that was a terrible vertical line. The last one is not vertical. Let's try that. There we go. Still not vertical, but closer. Okay, if you look at all this, okay, it only crosses the graph one time. There is not multiple points. Each vertical line crosses the graph in 1 point and 1 point only, one distinct point. So this is also a function. Okay, so how you determine it is once you've graphed it, if it only crosses it in 1 point, no matter where you draw your vertical line, then it would be fine. If you get a vertical line, it's going to cross it multiple times, so a vertical line is definitely not a function. All right, we have seen functions represented as equations involving x and y, such as y equals negative 3x plus 1. Below this is the same equation written in what we call function notation. Function notation, you just replace the y with the function, with the term f of x. It looks like f parentheses, it looks like f multiplied by x, but it's not, it's read f of x. So y equals negative 3x plus 1 is the same as saying f of x equals negative 3x plus 1. Right? The letter f is the name of the function. It's not a variable. Function notation is used to emphasize that the function value of x depends upon the independent variable of x. Other letters of f besides f can be used. You can have g of x, h of x, q of x, z of x, and or like the next problem we have t of x. So let's look at evaluating a function. It says the function t of x equals 65x represents the number of words t of x that Rachel can type in x number of minutes. In other words, she types 65 words a minute. How many words can she type in 7 minutes? So to evaluate this, we're simply going to put in t of x equals 65 times 7 because we're replacing x with 7. And then we're going to multiply it together. So t of x is going to equal 65 times 7 is 455 words. Okay, so Rachel can type 455 words in 7 minutes. All you have to do is just know that t of x or f of x or q of x is a fancy way of saying y equals. In English, we have lots of words that are synonyms to each other. This is like a synonym. It can replace the y. You can replace y with any letter of x that you want. And you can even have something like t of q or q of p. It all depends upon how the equation was written. All right. Finding the domain of a function, or excuse me, finding the range of a function. The domain of g of x equals 4x minus 12 is 1, 3, 5, and 7. What is the range? Basically meaning they want you to replace x with 1 and figure out what you get for g of x. Replace x with 3 and figure out what you get for g of x again. And there's two different ways you can do this. I like to make a table, just because we're used to making tables when we graph things, so we might as well write a table. So I'm going to have g of x, so I'm going to have x, and instead of having x and y, I'm going to have x and g of x. And we have 4x minus 12 in the middle. My range is 1, 3, 5, and 7, so x is 1, 3, 5, and 7. And I'm just going to replace x with 1 and figure out what g of x would be. So I have 4 times 1, which is 4, minus 12, which is negative 8. If x is 3, 4 times 3, which is 12, minus 12, which is 0. If x is 5, 4 times 5, which is 20, minus 12, which is positive 8. And if x is 7, 4 times 7 is 28, minus 12, which is 16. So my range then is all of the values I got for g of x, because remember, it's the output. The input was 1, 3, 5, 7. My output is going to be my range. Remember, we list them from smallest to largest, and luckily for us, they're in that order when we put them in our table. So we have negative 8, 0, 8, 16. So that is the range of this particular problem. Now, you could have done this separately as 4 different problems. I just like putting it in a table because it's so much easier for me to get all my answers in a neat and tidy format. The last thing we need to be able to do is we have to be able to identify a reasonable domain and range if given a word problem, a real world problem. Here we have, Lorena has 4 rolls of ribbon to make party favors. Each roll can be used to make 30 favors. The function f of r, see, notice I told you it can be something other than x, f of r equals 30r represents the number of favors f of r that can be made with r number of rolls. What are a reasonable domain and range, and what is the graph? Okay, so this is what we have to know. We know that r is equal to the number of rolls, and f of r is equal to the number of favors we have. Right? It says that she has 4 rolls of ribbon. Okay, so how many party favors can she make out of 4 rolls of ribbon? So our domain is what can we put in for r? Well, we can put in anywhere from 0 to 4 because we have, 0, we only have 4 rolls of ribbon. She can use part of a roll of ribbon as well. She can use 3.5 rolls of ribbon or 3 1/4 rolls of ribbon. So a good reasonable domain here would be that r is greater than or equal to 0, but less than or equal to 4. It can be between 0 and 4 rolls. Okay? And that's how and it's easier to write the domain is as a more like set notation and less like roster notation. Right? And my range is what am I going to get out if I have the difference here? If I use 0 rolls of ribbon, I'm going to have 0 party favors, aren't I? So I know that 0 is less than or equal to f of r, which is actually 0 is less than or is which is less than or equal. Now all you have to do to find out your range is figure out the 2 endpoints. If I use 0 rolls of ribbon, I have 0 party favors. If I use 4 rolls of ribbon, 4 times 30, it gives me 120 party favors. So my range is going to be 120. So a reasonable domain is between 0 and 4 rolls, and a reasonable range is between 0 and 120 favors. Okay? And it's probably best to write it in a form of set builder notation. Okay, now we actually have to graph this. So I'm going to graph this, and I'm not going to use partial rolls because I can graph that part. I'm going to concentrate on the whole number rolls. So I have R, and I have f of R. And we're going to do 30R. So if I have 0 rolls, 30 times 0 is equal to 0. If I use 1 roll, I have 30 times 1, which is equal to 30. 2 rolls, which would be 30 times 2, which is equal to 60. And 3 rolls, 30 times 3, which is equal to 90. And last but not least, if I have 4 rolls, 30 times 4, which is equal to 120. Okay, now obviously I'm not going to graph both my x and y axis by ones. Okay, my x-axis is actually the number of rolls. It's actually my r-axis, and this is my f of r axis. And this would be the number of favors. It's really hard to write sideways. Okay. My number of rolls I can count by ones. So 0, 1, 2, 3, 4. But my number of favors, I'm going to go from 0 to 120. So I'm thinking, let's see. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Yeah, I can count by tens. I'm going to label every other one. But I'm counting by tens. So there we go. I've labeled my axes. I have given you my scale, and now I'm going to graph it. So 0, 0 is right here. I actually should draw in my 2 axes. I didn't do that, but I should. So I should. Oh, I don't want it dashed. Silly me. How do I want it? I want it nice and solid. That's a little thick, but you get the point. All right, so going back to this, I have 0, 0, which is here. I have 130, 120, 30 is here. 260, 260 is there. 390, 390 is here. And 4, 120, 4, 120. All right, this is definitely a linear relationship. So I can draw a nice, and it is continuous data. It's not discrete because I can use part of a roll. I can't get part of a favor, but I can use part of a roll of ribbon. Okay, so therefore, when I draw these lovely lines here, and there's my lovely line. I can figure out how many rolls I'm going to use based upon, how many favors I'm going to have based upon partial roll usage as well. And the last thing we should do, always label it. This would be f of r equals 30R. So we found a reasonable domain and range. We figured out a table of values, and we graphed our function here. So that's a real-world relationship in which, and of course, since we know we can't have less than 0 roles, we didn't need to use any quadrant other than quadrant 1. Our closure question for today. How are functions and relations related? Be specific, please.